that equal sign here only valid if we have no measurement noises, and we also assume that the system is linear system, no nonlinearity, no uncertainties, then that equal sign is valid. Otherwise, you will get y hat. All right. So now, however, now using these equations, now we can predict the yk plus 1, but here you got to be careful now. Yk plus 1, k changes to k plus 1, then k minus 1 changes to k, and so on. You can write this way. However, now if we sub this yk from that yk, sub this yk from that yk into this equation, so this yk sub into this equation, then we can write these formulations. Now, I will explain to you why we want to do that. Simply that if I want to predict yk plus 1 from yk minus 1, yk minus 2 to yk minus p, just keep this yk minus 1, yk minus 2, yk minus p the same thing this y as this step, then I will be able to compute yk plus 1. That's the only reason. So now, so this is the formulations. If you look at this, if I know the alpha and beta, I know alpha 1, alpha 2 to alpha p, then I will be able to compute alpha 2 minus alpha 1, alpha 1, and here alpha 3 minus alpha 1, alpha 2. But you gotta watch out. You cannot change alpha and alpha 2 become alpha 2, alpha 1, because they are matrix. Okay? Alpha 3 minus alpha 1, alpha 2 means just like that. You cannot write in terms of alpha 3 minus alpha 2 minus times alpha 1. That's not true, because they are the matrices. Plus this alpha and beta, the dimension alpha and beta, you got to watch out the dimension alpha and beta. Alpha is always square matrix. This alpha. All right. Now, alpha 1, alpha 2 to alpha p, they are square matrix. They are square matrices. Their size is, the dimension of that, dimension is m by m. That's number output by number output. Alright? The beta 0, beta 1, beta p, they are rectangular matrix. They are rectangular matrices. On their side, their dimension is m by r, where r is number of outputs, inputs. All right. So the dimension is like that, and now we have this one alpha 2. So here we can compute y plus 1 equal to this, and so on. Now the beta 0, beta 1 to beta p, they can be square if m equal to r. That number input equal to number output. Normally that's not the case. In general, we always got more output than input. Okay, now let us continue. So I define a matrix, a new notations. There's alpha 1, then super parenthesis 1, alpha 2, super parenthesis 1, that 1 is equal to that 1, k plus 1. That 1 means k plus 1, so that's the 1 here. Then we will define beta 1, parenthesis 1, beta 2, parenthesis 1, and parenthesis 1. That just, again, that's, I have a 1 here. This is the formulations, and I will show you the formulation. This formulation is very interesting formulations. Okay, let us look at the k plus 2. Now look at k plus 2. Now k plus 2, we have k plus 1 like that. K plus 1 equal to minus alpha 1, parenthesis 1, yk minus 1. Our yk is gone because we sub into it. Instead of that, we have alpha 1, parenthesis 1, alpha 2, parenthesis 1, and so on. How about yk plus 2? Now yk plus 2, we can sub in here. K plus 1 becomes k plus 2, and so on. Then we can use the same formulations, and we can sub yk into it, and then we form another formulation called yk plus 2. Then I have alpha 1, 1, and so on. You look at this formulation, almost identical to the one in previous slide, except now here is 1, 1, 1, 1. All right? And I will show you why I want to do this very soon. There's a purpose of that. Now, if you look at k plus 1, k plus 2, and yk plus 1 and yk plus 2, look at this. If I want to assume if you look at k plus 1 and k plus 2, yk plus 1 and yk plus 2. Alright. Now, look at this is I can look at this as my future output. Assume I give the data up to only yk. Assume you know the data up to only yk. That's all I know. And I don't know my data after yk, so I can predict my yk plus 1, yk plus 2. But however, I have the data only up to yk. We have output data up to k. All right, and also input data up to k. Now k can be 1,000, k can be 100. It's up to you. So because I know the data only up to yk. So I have to compute yk. This yk, I have to compute yk in terms of yk minus 1, yk minus 2, and to yk minus p. All right, the same thing. I want to compute my yk plus 2 also up to in function of k minus 1, k minus 2, and yk minus 2, k minus p. And so I want to say, okay, I want to say yk plus up to, maybe say p, all right, up to p. And I want this, or I can predict from those I know. All right, so how can I do that? And also I want to, then I give the U also, let me write this in terms of U, all right? Okay. So I want to predict yk plus 1, yk plus 2, yk plus b in terms of yk minus 1, yk minus 2, yk minus b, and uk minus 1, uk minus 2, uk minus b. Can I do that? Is there any way to do that? All right. So, however, all right, that's the step I'm working on. So if you look at this carefully, yk plus 2, I can predict yk plus 2 from yk minus 1, yk minus 2, yk minus b, and uk minus 1, uk minus 2, uk minus b. However, I still have to know this in the middle size, in the middle place here. That's called uk plus 2, uk plus 2. All right. So that we have uk plus 1, uk plus 2, and so on, right? And I call this is the past input and output data. And this I call future input data. Okay. So I have past input output data. I have a future input data, and then how can I compute the future output data? So that's what I'm going to. That's what I'm doing here. So then here in the chart here, after I compute it, because I have k plus 2 here, I define my notations to alpha 1 parenthesis 2, that's corresponding to this 2, alpha 2 parenthesis 2 corresponding to this 2, alpha p parenthesis 2, that corresponding to k plus 2 and this 2 here. All right, if you continue this is nothing but just an algebra. This is now, there's no differential equation here, there's no integral equation here, it's simply just algebraic equations. I think everybody knows how to do it. You just suck all those data in there, and you will be able to predict up to k minus 1 and k minus 1. I have alpha 1 k minus 1 here, parenthesis, alpha 2 and alpha 2 parenthesis k minus 1 there, then so on, alpha p k minus 1 here, and you can compute it just like what I did in last slides. And again, I have 1 k minus 1 here, 1 k minus 2, I equal k minus b, that's my past output. I have u k minus 1, k minus 2, k minus b, that's my past input. And then I have, in middle here, I have k here, k plus 1, that's my future input. So, my future output, I can predict it from, I can estimate it. Well, in theory, I need to have a head here, but I don't, as an economic head. I assume that this system has a noise free, and the system has no uncertainties and nonlinearity. And there's a future input in the middle of the future output, and in the past output and past input, like that. Okay, now let's use this. I can compute that too. So that's, and I can k plus q, and again this is from y minus 1, y minus 2, and k minus 1, k minus 2, and k minus b. The past output, past input, and then future input. I will tell you why. Very soon about this. And then let us look at the look at definition. See, if I have a q here, then I have a parenthesis q here. I have parenthesis q there, parenthesis q there, and again, I'm involved on the past input, past output, future input, and future output. Then I'm going to explain to you just next